Light has been a mystery for centuries. Light is fascinating, driving away darkness, bringing warmth and joy to our day, and guiding everything we do. But historically, the nature of light was not obvious to establish. Christian Huygens was one of the greatest scientists of the 17th century, among other famous names like Descartes, Pascal, and Newton. He was the first to identify the nature of the rings of Saturn. He was also the first to lay out a wave theory of light, published in 1690, in French. Okay, let's spend 1 minute on the theory and what is the meaning of wave diffraction and interference. And then we'll jump right into the experiment. Photons, electrons, and any particle can behave as a small lump of energy or as a wave. This dual behavior is known as the wave-particle duality and is at the heart of quantum mechanics. To show the wave aspect of light, we are looking for a diffraction pattern. If a wave is going through a slit larger than its wavelength, it will create a diffraction pattern. So a beam of light composed of parallel waves will enter the slit, and at this point waves will go in several different directions. Then, depending on where the waves are meeting on the screen, they can travel the same distance, like in this case, and here they add up their intensity. Or they can travel a different distance, and if the delta is just half the wavelength, then they cancel each other, which is why, as we go away from the middle of the screen, we have a pattern of light spots and areas with no light in between. It is amazing to realize that we can demonstrate this property, characterize and visualize the wave aspect of light at home and with very simple material. We need a screen to visualize the diffraction pattern, a laser pointer, or two if we want to test different wavelengths. I will use a caliper to create the slit. And finally, an open space in a garage or anywhere really. Let's set it up now. We need to use a laser pointer and not a flashlight, for example, as we do need a single wavelength and a coherent light. Otherwise, multiple patterns of diffractions would be mixed and we wouldn't be able to see anything. Okay, lights off, we are ready to go. We just need to pinch the caliper so we have a very narrow slit, about the wavelength or slightly more. Then we adjust the laser beam so it goes straight into the slit. It looks perfect now and we can just check it out. Hey, look at this fantastic diffraction pattern. It is beautiful and I was probably lucky when adjusting the slit, making it the ideal width, about a few wavelengths. We can clearly see the different spots of light and the dark areas in between, where the light waves are cancelling each other. Now I'll make two small variations of this experiment. First, by adding a horizontal split. So we have a square hole, just to check that we have a cross-like pattern of diffractions. It looks like it is working exactly as expected. Let's check it out on the screen. We have the horizontal and vertical diffractions, following the edges of the square hole. But as you can see, it is not as crisp, obviously because I used Scotch tape. So the quality of the edges is not great. And a final variation using the red laser, which hopefully will give the same diffraction pattern. So we can definitely conclude that light is a wave. Yes, of course, another very nice diffraction. No doubt, light is a wave. Alright, that's it for today. I leave you with this incredible diffraction picture obtained very easily in my garage. I'll be working soon on my next video, which I think will be about gravity and how to experience zero-G, like in space, but here on Earth. That sounds promising. Okay, if you enjoyed this video, please subscribe, make sure you click the thumbs up and hit the notification bell so you know when the next video is coming. Take care.